Okay, good morning, everyone. Today we're going to start the actual course. So we're going to be starting with section 6.2. But before we start, I would like to make a small remark about the quiz. One problem you guys had some difficulties with. I mean, every student have different kind of difficulties, but one of them was number 3, part A. Okay.
I do not have the mental capacity to learn calculus right now.
All right. So the problem was the following: integrate. It's 1c, if my memory is right. 2c, sorry. Integral from 1 to e of 1 plus the square root of that dt. Okay. And I gave you a hint. I told you set u to be ln of t. Okay. And the u will be 1 over t dt. Okay. The remark is when we do substitution, we substitute everything. We substitute carefully. We don't let things, we don't drop things or anything like that. So what do I mean by this? This is going to become the following. If I change the limit, so if t is 1, u would be the ln of 1, which is a 0. And if t is e, u would be ln of e, which is 1. So this will become integral from 0 to 1. And dt over t, this piece, will become my du. And then it's the inside, and that's where a lot of you actually had problem. This is 1 plus the square root. So when you substitute, the 1 stays. The 1 doesn't go. It is a 1. You cannot just out of the blue throw 1 away. And the square root of log t will become the square root of u, du. That's what will become as an integral in u. Okay, so one mistake a lot of you did is by letting this 1 disappear, you cannot let it disappear. 1 has to stay. It's a 1. You're basically thinking what you're substituting term by term. Equal. Now, the other mistake you did was the following. This is a new integral in u. The variable is u. So when you're finding the antiderivative, 1 is antiderivative is u. Some of you, when they integrated 1, they went back to t. And that's really wrong because you think about it that u is your new variable now. So antiderivative of 1 become a u. Antiderivative of square root of u, that's no problem with that. Evaluated between 0 and 1. And then the rest become fairly simple. Okay, so it's 1 plus 2/3, which is minus 0, which is 5/3. Okay, so the two mistakes that came up were, the first mistake is that when you make the substitution, you substitute verbatim. So the 1 doesn't disappear. A lot of you, the 1 disappeared. Mistake number 2, once u is your new variable, antiderivative of 1 du is u now, because u is a variable. It's not t anymore. Okay, so this is a remark about the problem in the quiz that actually gave you a hard time. Okay. All right, so today, as I said, we're going to start section 6.2, area between two curves. So section 6.2. Area between two curves. Okay. So let us recall what we know concerning this topic. What we know so far is the following. If a function f of x is positive, that's what we know, on an interval AB, so that's the picture that we're familiar with. This is a function, it is positive, and that's crucial here. That's A, this is B, and this is my function f of x. So if my function f is positive, then the area under the curve means this area under the curve of f of x is the integral from a to b of f of x dx. Okay, so the area under the curve is the integral. And the reason why it is the integral, it's not the integral actually. The area is nothing more than the limit of those sums. So what is this whole thing was coming from? We actually subdivided the interval into pieces. That's verbatim what we did. And what we actually did, we took f of x0 times delta x, that's x of 0. It gave me the area of this. I added this area. That's basically what we did. Plus, we kept adding. And if I'm taking the left sum, that was the last rectangle I took. This gives me the sum that is an approximation of the area. That's the approximation. That's really was our logic, which is basically the sum, and we wrote this in sigma notation, which is equals 0 to n minus 1, and that's what we call the Riemann sum. And the actual area is basically what happened to this sum when we take a lot of subdivision. So it was the limit of those sums. What happened to those sums when the number of subdivision n becomes very large? We express this by saying the limit. And this is basically what we call the definite integral. So that's what we know so far. So if we want the area under the graph of a function, okay, the area is we approximated by the sum of the area of the rectangle. That was our logic because we don't know what else to do. So we filled it with rectangle. We approximated by the sum of the area of this rectangle. Every piece here is an area. Every piece here is an area. And then we said when n is large, we cover the whole region more and more. Therefore, the area is what happened when n is large. And we define this to be the integral. Okay, so that's what we have so far. So the area under the curve is given by an integral. Today, what we're going to do is the following. Instead of taking the area of one region, what we are going to do is basically take the area between the graph of two functions, something like that. So we have a function f here. We have a function g here. And we have a and b, and we're going to take the area between them. That's the problem we are going to take care of today. All right, so anybody, any idea what's going to be the area?
Maybe we're going to take both of them, do the area between both of them, like how we did with the last problem, and add them together.
I'm going to give you an easy scenario. An easy scenario, then I'm going to go to the harder scenario. You don't have to write. I'm just talking now. Suppose I take f to be like this and g to be down there. This is A, this is B. Okay, so the bottom is G, the top is F. Okay, and I ask you to find the area between them. Is this a hard or an easy problem? What do you think? Okay, this scenario is just the one I'm going to work with, but let me give you a very easy scenario. What do you think this area would be?
The integral of f of x minus g of x.
Yeah, why? You're right, if you explain it.
Because the f of x includes that bottom part of g of x.
Absolutely correct. Okay, here's your classmate. She's telling me, all right, in this easy scenario, take the integral from a to b of f of x dx. This will give you, both f and g are positive. This gives you the area of this region in red. Take away from it, she told me, take away from it the integral from a to b of g of x dx. By taking that away, as she said, I'm taking away this piece right here. All right, that's her idea, which makes a lot of sense. What I'm left with is the area in between. Now, another way to write this is the integral from a to b of f of x minus g of x dx. So this is, I call this simple scenario. That's the simple scenario. So in this simple scenario, the area is very simple. It's the integral from here to here. Now, here it's become much harder because the integral of f is under the curve because f is positive. But the integral from a to b of g is problematic because g is not positive. It's positive, it's negative, it's positive. So the area here become really, really problematic. So I cannot really apply this immediately. So how are we going to do that? All right. One thing, this section is easy, but it set the stage. The way we're going to think about ideas in this section will set the stage for the following 3 sections. So I'm going to take my time explaining. Okay. I don't want you to write yet. Just want you to keep following. The idea is the following. If we have an area, we have no idea how to approach it because I gave f positive, g negative. The problem is problematic. Our idea would be to approximate this area with some of area that we understand. Now, what's the simplest area we know? The simplest area we know is basically rectangle. That's what you really know. So the idea is to fill this region with rectangle that we can find their area very easily and approximate this whole area by those rectangles. So which rectangle we are going to take? The rectangle we are going to take are the following. We're going to take this piece divided, AB divided into pieces. I don't want you to write now. I'm just trying to explain the idea. So this piece. Now I'm going to fill the region. I took finitely many. So I'm going to take this x0, x1, x2, x3, x4, x5, x6. Okay? And then we're going to take the following rectangle. The first rectangle is the following. The height is going to go from the bottom curve to the top curve. And the width is this little bit here that we call the delta x. That's going to be the width. That's my first rectangle. My second rectangle is going to be the same. Watch how I'm going to do it. I'm going to go from the bottom. I want you to see exactly what I'm going to do. All the way to the top. So from the bottom curve to the top curve is going to be my height. And my width is going to be this delta x. That's my second rectangle. My third rectangle, the same thing. From the bottom curve to the top curve, this is my delta x. Okay. And then I'm going to keep verbatim the same from here to here. The delta x is going to be the width. The height is from the length from the bottom curve to the top curve. And then I keep going from the bottom to the top. This curve, and then I'm going to do verbatim from the bottom to the top, and this is my width. So that's really going to be the idea. I'm going to approximate the area by the sum of the area of those rectangles that we're going to find their area very easily in a second. And then I'm going to add those areas. I do it first by filling it with 5 rectangles, then 6 rectangles, then 100 rectangles, then 1000 rectangles. The more rectangle I have, the better I have the approximation. And then I'm going to add their sum. So that's really the strategy that we are going to follow. Okay, any questions? All right, so step number 1 is, what is the area of each one of them? So before I start again, let me talk a little bit about something. Okay, any questions? Okay. Let me talk about a simple idea. Let us say I have a line here. Okay, and this is 0, so that's a vertical line, this is 0. And I have 2 points on the line. Let me call this C, for example, and D. Okay. My question to you, what's the length from here to here? Quickly.
D minus C.
D minus C. D, take away C. Okay, no question asked. Now, let us say I make my scenario a little bit harder. I put 0 in between. I put C here and D here. Okay, my question is, what's the length of the segment from here to here?
D plus C.
I disagree. What? That's your idea, D plus C, right? Why I have a problem with it? Let's take example. Suppose this C is -2 and this D is 3. Is the length from here to here 3 plus C?
So
it's still D minus C.
It's still D minus C, and let us see why. And let us see why. Because my idea is that regardless how the points are located, why it is D plus C. From here to here, it's a D. I will write this in red. Correct? That's a D. What's the length from here to here? If C is negative, like a -2, the length is actually the negative of it, simply because C is negative. So the actual length is negative C. So from here to here, I have D plus minus C. It means D minus C. It's the top value minus the smallest value. Okay, so regardless where the points are, whether 0 is in between or not, the distance between 2 points on the vertical line is the actual higher value minus the lower value. We can make the same logic even if my scenario is like this. Suppose this is a 0. Even if my D is here and my C is here, both of them negative. So both of them negative. And what's the length from here to here? It's a little bit harder, but the formula actually is the same. What's the length from here to here?
D minus C.
Yes, because how much is that? From 0 to C. What's the length here quickly?
Negative C.
Negative C, because C isn't positive. What's the length from here to here? Sorry, my apology. From here to here.
0 minus D.
0 minus D. So what's the total distance now? It's minus C. This one. You take away from it the top part, which is gonna give me minus C plus D. It means D minus C. So what is the conclusion? If you have 2 points on the vertical line, the distance between them, regardless how they are located, above the x-axis, below the x-axis, one above, one below, regardless how they are located, the distance between them is always the upper value, if you want, minus the lower value, regardless whether the points are of their location, okay? And this is the idea that we're always going to use. Now I go back to my problem. Again, I go back to my, to this problem, here the picture, and then I'm going to generalize. So before I generalize, I want you to fully understand what I'm doing. What's the area of this rectangle? What's the area of this rectangle? Help me out. What's the coordinate of this point down here? And what's the coordinate of this point down here? Right, this is f of x0.
Function of x0 times delta.
Right, and this here is f of x0. So the area of this rectangle, so the area, let me call this, give me a name, let me call this R1 if you want. Sorry, I call this R1. I call this R2, R3, R4, R5, R6. So what's the area of R1? It's f at x0 minus g of x0 times the delta x. So the area is f of x0 minus g of x0 times the delta x. That's the area of R1. What's the area of R2? What's the area of R2? Should I pick one or you guys are ready to answer?
f of x at 1 minus g of x at 1
Right,
times
right.
delta x.
Yeah, it's f of x 1 minus g of x1 times delta x. What's the what's the area of R3? So I wanted to see if that we're gonna basically repeating ourselves. Times the delta x plus the area of R3 is always the length from here to here. This length is the value of the function at x2, sorry, it's f of x2 minus g of x2, so that's the area, times the delta x. R4 is the same, R5 is the same as R6, really the same. And the idea will be we're going to add all those areas and then take the number of subdivision larger and larger and see what we get. So that's really the principle that you are going to be based on. And now I will treat it in the most general case. Now I move on and I start the generalization of this idea. So area between two curves. So this is my problem. Okay. Let R be the region. So let R be the region. Bounded from above by the graph of f equal f, by the graph of y equal f of x. So that's above. Below by the graph of y equal g of x. And the lines x equal to a and x equal to b. That's really my region. The question is, goal is to find the area. First, let me read this and see what they are talking about. R is the region bounded from above by the graph of f, below by g, and the lines x equal to a, x equal to b. So what region are we talking about? We're talking about the following kind of region. So this is my region here. I have from the top f of x. So this is f from the top. From below, g. That's the bottom curve. The lines x equal to a, remember those are vertical lines. Means this line and this line. And this is my region R that I like to find its area. Okay, in the previous example, I divided R into like 6 rectangles, and because I was trying to explain the idea. Now, in general, the way we're going to do that is we're going to divide the interval AB into n equal subinterval. So that's the general setting, n equal subintervals. And delta x is the length of each one. So it's very tiny because n should be very large of each subinterval. Okay. So I'm going to do exactly like last time, but now it's a general scenario. So I'm going to cut this into subintervals, n of them. So I'm going to put etc. because it's harder. So this is my x0. This is x1, x2, x3, and etc. So I'm dividing it into n subintervals. And this one here is xn minus 1. So in general, I'm going to call, so x3, x4, x5, I will call this xi, and I will call this xi plus 1, because I'm not going to really cut all of them. And the idea is like before. I'm going to cover this with a rectangle. So that's my rectangle. Delta x is the width. The height is from the top curve bottom to top. The height starts from the bottom to top. That's the height. From the bottom to the top. That's my rectangle. Okay, that's my rectangle from the bottom to the top. Okay, so in general, a typical rectangle will be the following. My typical rectangle, and we're going to use the word typical a lot. My typical rectangle starts from the bottom curve. So that's a representative for each one of them. And this is the delta x. That's what I will be calling a typical rectangle. Okay, and this is right here. Okay, so this rectangle here, we're going to give it a name, and this we're going to call it typical rectangle. Means it's a representative for all of them. Okay, that's we call typical rectangle. Now, I call this R1, R2, R3, R4, Ri, and Rn. Now I'm going to compute this area of each one of them and then add them. But since all of them look like this rectangle, I'm going to focus on the area of what I will be calling typical rectangle. So what do I mean by typical rectangle? It's the rectangle that represents every one of the other one. That's what I mean by typical rectangle. It's the representative for everyone. What's the area of a typical rectangle? It means of Ri. It's equal to what? The height from here to here times the width. Now, what is the height of this rectangle? What is the height? Area of typical rectangle. The height of a typical rectangle is equal to, you can give me the formula quickly. Who's comfortable to give me, not f of x, be very careful. What's this point down here? This is xi, g of xi. And what's the point up here? So this right here is g of xi. This point here is f of xi. I'm focusing on one rectangle that I'm going to call it the typical rectangle. So the length is going to be f of xi, the height, sorry, minus g of xi. So the area of a typical rectangle, the height is the value of the function at xi minus g of xi. Okay. Typical, it means that if I take the first one, is f of x0 minus g of x0. The second, f of x1 minus g of x1. F of x2 minus g of x2. So instead of doing everyone by itself, I focus on the typical rectangle and I find its height. The width is delta x. So the area of the typical one is f of xi minus g of xi times the delta x. That's going to be the heart of what we're going to do. So we're going to focus on one of them, what we call the typical one, and analyze it. Now, what's the area of the whole region? The area of the region is almost equal to, the area of R1 plus area of R2 plus, etc. Area of Ri plus so on, area of Rn. So we're approximating it. The area of the first plus the area, plus the area, plus the area, plus the area here. So this is going to be equal to, so I know it's a little bit tedious, but that's okay. Plus, so I'm adding area. Plus, I'm adding area. Plus, I'm adding area. Now, the first one is f of x0 minus g of x0. The second one, f of x1 minus g of x1. It's the same formula. F, the typical one, xi minus g of xy. And the last one is f of xn minus 1 minus g of xn minus 1 delta x. So that's the area. Now in sigma notation, because it's tedious, it's clearly tedious, but that's the idea. I'm adding areas. So the area is almost equal. In sigma notation, is the sum of those little areas. So we're adding little areas. Each one has the form, that's the form of each one of them. Xi, gi, delta x is the width. And my I goes from 1, in this case 0 to n minus 1. Remember, that's the height of the rectangle times the width. Okay? All right, so that's an approximation. Now, the idea is as n gets larger, the areas, the sum of those areas become closer and closer to the actual area. So when n gets larger, much larger, the Riemann, so this is actually, if you recall very well, this is actually look like a Riemann sum. This look very much like the Riemann sum. Well, this is my function, f of xi minus g of xi minus delta x. So as n gets larger, the sum of the approximating rectangle become closer, and so the sum of the approximating rectangle is closer to the actual area. Okay, as we get more and more subdivision, we're getting close to the actual area. So what's the actual area now? The actual area is going to be what happened to those sums when n becomes very large. F of xi minus g of xi, I equal 0 to n minus 1. Okay, so the actual area is what happened to the sum of those approximating when n goes to infinity. But now I'm gonna definitely relate this to the notion of definite integral, but that's equal to what? Remember, if we look at this very carefully, this looks exactly like a Riemann sum, where this is the function. That's a Riemann sum of this function. And this is nothing more than the sum. So it's going to be the integral of f of x minus g of x dx. And the boundary are the interval that I had to divide into pieces to be able to cover my whole region. It's going to be the integral from a to b of f of x minus g of x. So that's really the hard part, that recognize that this sum is a Riemann sum. Of which function? Of the function f of x minus g of x dx. The limit are represent, the upper and lower limit are what I need to divide into pieces to cover the whole region. And I need to divide the interval AB. That's the one I divided originally to be able to cover those pieces, and this will be the upper and the lower bound. Okay. So let us summarize this in a box. But the box. So what is to summarize this? Summarize this is the following: the area of the region. So the area of the region. The area of the region, bounded from top by y equal f of x, bottom y equal g of x, the lines x equal a and x equal to b is given by the integral from a to b of f of x, which is the top curve. So usually I write yt to remind you it's the top curve, minus g of x, which is the bottom curve, dx. Okay. So that's really the idea. So now we're going to do at least 2 examples before I let you go. 2 examples. And the way I'm going to do the examples is in details. And let's see what do I mean by details. So I'm going to take my first simple example, the following. Can I move on? Everybody ready? Can I change the page?
Yes.
Yes, no, anybody? Yes, thank you. All right. I'm going to take my first problem. It's very easy in nature, but it will explain to you how I would like you to think about those problems. All right, so this is my example. Find the area, if you guys are writing, I will be slow, of the region bounded by the graph of y equal ex, y equal x minus 1, and the lines x equals 0 and x equal to 2. So that's really my problem. And do the problem following the steps below. Okay. So we want to find the area, but I want you to find it by following the steps. Sketch the region. Is sketching the region necessary? Yes or no? Back to you.
No.
Not really. No.
No.
Why? No.
Because we already have the
You have all
equation.
new.
Which is the top, which is the bottom? So if you want to use the formula, what do we need to know? Which is the top curve, which is the bottom curve. So without sketching, I have no idea which is the top, which is the bottom. All right, so sketching the curve is absolutely crucial to do this problem. So whether I tell you or not, I have no idea which is the top, which is the bottom. So this is a crucial step. So we want you to do that. Second, I want you to draw a typical rectangle. And I will explain again what I mean by that. Label it and find its area. So I want you to know what we are doing. 3, I wanted to write the Riemann sum that approximate the area. I want you to see that what we're doing is adding the little area. The last step is express the area as a definite integral and then evaluate. So we're going to do this problem exactly step by step so we understand the concept that we are working with. Okay, so first we sketch. We're going to draw the typical rectangle, add those areas, and then express this. So let us go and do that step by step. So step 1, I'm going to graph the function. What are my functions? Y equal ex, y equal x minus 1, the line x equals 0, x equal 2. Now, y equal ex, we should know how ex looks like. Ex go like this. So, and I want it between 0 and 2, so this is the graph of y equal ex to the x. Now, so that's y equal ex. Then y equal x minus 1. Y equal x minus 1, that's nothing more than a line. At x equals 0, it's a minus 1. And then it's a line. Go like this. And then between x equals 0 and x equal to 2. X equal to 0 is this line here. Now, if we are very careful, that's 1, and x equal to 2 is this line up here. So this is the region that I am interested in. Is that clear? Crucial. So my top curve here, now I know which is my top curve is EX, and my bottom curve is X minus 1. That's sketching the curve. So that's my region. I understand it very well, between 0 and 2. Question number 2. Draw a typical rectangle that we are going to use to approximate the area. Draw a typical rectangle, label it, and find its area. What am I asking you here? Remember how we're going to do it. We're going to basically divide this into rectangle. So I'm going to call this typical rectangle. So basically in my mind, this is the xi point, and this is the xi plus 1. So basically we are dividing into pieces, and that's my representative for all of them. Now what's my typical rectangle? It's the rectangle that go from the bottom to the curve. That's the kind of approximation I'm doing. The width is the delta x. The delta x is the length of this little one. This is really my delta x. Okay, that's the width. And that's my typical rectangle. So that's what I call the typical rectangle. That's the one that we're going to add rectangle like that. Now, we're going to find the area of the typical rectangle. So what's the height? The height is from here to here. That's the height of my rectangle. So area of typical rectangle. Okay. The height is equal to, all right, what's the height? The width and the area. What's the height? This point here is what? This is xi. This point up here is xi, e, xi. So this point here is exi. This point down here, it belongs to this curve. This curve is x minus 1. So this point is xi minus 1. So the height of my rectangle, so the height, which is in red, the height is exi minus xi minus 1. So the height is the top curve minus the bottom curve right there. This is exi, it's xi minus 1. The width is the delta x. The area is the product minus the lower curve. Okay. So that's the height from the bottom to the curve. So that's draw a typical rectangle, label it, and find its area. That's what I mean. Now part 2 is write the Riemann sum that approximate the area. What I have in my mind right now, which picture I want to emphasize now. When I write Riemann sum, it means I want you now to start thinking that what we're doing is adding those areas, adding those little areas, then taking the limit. That's how we are thinking. So part 3i is write the Riemann sum. What does it mean by writing the Riemann sum? So basically, what I have in my mind means the area of the region R is almost equal to the sum of the area of the rectangle. Almost equal. It means every rectangle, now that I'm writing my Riemann sum, has for area something like that, where the xi changes. So it's sum of e dxi minus xi minus 1 delta x. That's the Riemann sum. It means the sum of the area of the little rectangle. That's really the idea here. Finally, express the area as a definite integral and then evaluate. So finally, we're gonna finish the problem. What's the total area? I know it's tedious, but it's good training for you. The area is actually what happened to those sums when we take a lot of subdivision. That's really the picture in my mind. minus this delta x. Now I want to write this as an integral. That's the following integral. This is the function. Ex, at this stage, no more xi because I'm inside the integral. X minus 1. Delta x is the dx. And now the upper and the lower limit. Upper and the lower limit, you go back to your integral and ask yourself, what did I divide into pieces to cover the whole region from 0 to 2? And always the formula, we know what the formula is, but how we got to the formula is exactly what we're doing. So that's the top curve and that's the bottom curve. So in case I don't ask you to do everything in details, you know the formula. If I ask you, which is I will, we have to go through the step. Now, finally, we need to evaluate this. All right, evaluation is easy. This is the integral from 0 to 2. First, I need to simplify inside minus x plus 1 dx. So it's equal to ex minus a half x squared plus x evaluated between 0 and 2. And this is going to give me e squared minus 2 plus 2 minus, at the lower, e to the 0 minus 0 plus 0. So it's going to give me e squared minus 1. End of the problem. Okay.
Could you show the steps that you had written down on the last page real quick?
Sketch the region. Draw a rectangle, label it, find its area. Write the sum, Riemann sum that approximated, and then express the area as a definite integral.
Thank you.
Okay, so we're gonna very quickly do
question.
another. Go ahead.
Can you just
Question.
go back to the last part real quick?
I will go to every part.
Revalue, just revalue, okay. Okay, thank you.
Sure. Very quickly, another problem, and I'm going to follow the same step, but of course, I will go a little bit faster every time. Now, the question is, find the area of the region. Bounded by the curve y equal to x and y equal x squared minus 3x. And the question is following the same step as before. So what's the first step?
Sketch curves.
What? Repeat.
Sketch the regions.
Exactly. I have no idea what's really going on right now. I have no clue. What's up? What's bottom? I have nothing. I don't know anything. So the first step, check the region, sketch the region. Crucial. All right, what's the region? Y equal to x is just a straight line. We should know it. And I don't know if it's the top or bottom yet. I mean, I will label it the minute I know what it is. X squared minus 3x. Okay, x squared minus 3x, that's a parabola going up. Sometimes an easy way for me to draw a parabola, especially in those problems that are not hard, I try to find its zeros. I said, okay, when is it 0? So I factor it out. I realize x equals 0 and x equal to 3. So we know it's a parabola going up. It's 0 at 0. It's 0 at 3. So how it's going to look like? It's going to look like that. Okay, this is 3. Okay, so now let me read the region again. It's the region which is bounded by y equal x squared minus 3. That's the region in question. Okay, now, what do you think I need to do second? Usually the idea is that, what do you think I need to do second?
Draw the typical rectangle, or you label actually next and then do that.
Yeah, but one issue in this, I don't know what the boundaries are. So to be able to, which interval I need to divide into pieces to be able to cover the region, I really don't know it yet. So in this particular problem, I need to find basically the A and the B. I need to find those points. So how do I need to find the point? What do I need to find in this particular problem? How do you think I find this point and that point? What do I look for?
Do you set them equal to each other?
Exactly, because what do I need to find?
Their intersects.
Exactly,
Intersection.
intersection point. Otherwise, I really don't know what this point is. All right, as your classmate said, how do we find the intersection point? We said the y's equal to each other and we solve for x. So find the intersection point. I want to set x squared minus 3x equal to x and solve for x. This is a quadratic. The only way we solve quadratic is somehow to make it equal to 0. So I need to bring this x here. Minus 3x minus x is going to give me minus 4x. Now I factor out my x equal to 0. It's going to give me x equal to 0, x equal to 4. Crucial. In this problem, without this, I still don't know what my limits are. So this is my 4. So this point here is a 4. And the y-coordinate is a 4 also because it's the line y equal to x. And this is a 0. Okay, so now I have a better picture of what I am dealing with. Now, I'm going to take a typical rectangle. If I don't ask you to do typical rectangle, you don't have to. But if I do, you have it. So now I take my typical, this is my rectangle. This is the rectangle. That's what I call the typical rectangle. And now I want the height of it. And I want the width. The width is easy. It's delta x. That's the width. Now what's the height? It's the value of the upper curve. It's this one minus this. That's really what the height is. This is xi because that's the graph of y equal xi. So whatever xi is, from here to here, I have also xi because that's the graph. Down here, it's the bottom one. So that's the top. And the bottom one is x squared minus 3x. So this is xi squared minus 3xi. So whatever the value of xi, the value from here to here is this. So the height is going to be the value at the upper curve minus the value down here. The width is delta x. So that's really the picture. Once you understand the picture, believe me, a lot of things become way easier for us. Okay, so now, area of a typical rectangle is the height times the width. The width is the delta x. The height is xi minus parentheses xi squared minus 3xi. That's every rectangle. Part 2 is the sum. It means the total area is obtained by adding those rectangles. At this stage, I'm thinking about subdividing all of it and adding the area of each one of them. So now in sigma notation, this would become sigma of this. So now I am adding the rectangles in my head. xi minus this. Okay. Finally, I want the Riemann sum, sorry, the definite integral equal. Now, the actual area is what happened to those sums when n becomes very large. Sorry, that's a minus in here. My apology. That's a minus. Okay. What happened to those sum when n is large? When n is large, what happened to the sum becomes a Riemann sum, which become a definite integral. And definite integral of which function? X minus. The x represent this width, and this is the bottom curve. At this stage, there is no xi because the integral represents those sums. And the bottom limit is 0. The upper limit is 4, because I have to divide the interval from 0 to 4 into pieces to cover my whole region. And that's it. And the rest is simple. So that's the integral from 0 to 4 of x. I simplify the inside a little bit, minus x squared plus 3x dx. So that's the integral from 0 to 4. Of 4x minus x squared dx. And now it's a simple integral that we shouldn't have any difficulties computing. Antiderivative of 4x is a half x squared. Antiderivative of that is minus a third x cubed between 0 and 4. And finally, I get the following. But at this stage, it's simple. I evaluate at the upper limit, 4 squared minus a third 4 cubed, the whole thing minus the value at the lower limit, which is equal to 0. And finally, I get 32 minus 64 over 3, which is how much? 6, about 96 over 3, which will give me 232 over 3. Give and take a stupid mistake at my head. Okay. All right, that's it for today. Your homework is already on MATLAB. So for those who have MATLAB, I know that most of you, I still have like 6 students who don't have it. So please, those students get it. And I will put it at the same time on Brightspace. So for those who have the book, they can do the problem from the book for now till they get the MATLAB, and then they have to do it on MATLAB. And for those who have their MATLAB, it's already there, get started. Okay, and starting today, the homework will be graded on my MATLAB. Any questions? Okay. As you know, you may struggle with the problems, which is okay. You just have to ask me tomorrow, and tomorrow we will do, as usual, we do a lot of problems. I answer all your questions, and we introduce a new idea. Any questions? Yes, Freddie, yes. Anybody else?
I have a quick question.
Please go ahead.
On MATLAB, I don't see the assignment open yet.
You don't? I checked
no.
it. I thought I
Alright.
opened it long time ago. I will check
Yeah.
it now. Yeah,
All right,
I
thank you.
definitely do. I will definitely do because I thought I did. Anybody else?
For the Riemann sum on the example problems,
Yes.
you have used left Riemann sum.
Yeah, it
Is
doesn't
that
matter.
specified?
No, you don't. It doesn't matter what to use.
Okay.
Okay. Now, here's the thing. MATLAB doesn't ask you to do that, but I will ask you. Is that clear? MATLAB doesn't, but I do, because I think it's very important for you to understand the concepts. MATLAB only emphasized, the formula, and that's not really my goal. So you have to learn how to do it.
Okay, thank you.
Other questions? So I will check my lab now, right? Once I finish. I'm still trying to get my book and access to my lab. Okay, anybody else? Any questions? Freddie, I'll talk to you later. Any other questions? Okay, you guys can leave the meeting because I have to talk to one of your classmates.
I also don't have any assignment on my lab. So
It's then it's my mistake.
Okay.
I will check it immediately right
All right,
after
thank
I
you.
finish with you. Definitely so.
all right,
But sorry about that. I thought I did.
okay, that's fine.
Okay, please, the meeting ending, except for one student that I need to talk to him in private. So Jacob and Andre, do you have any question? Jacob? All right, Freddie, can you talk? Freddie, do you have a microphone? Yes, so can you tell me what's happening? Did you go to Pearson's website?
Can you hear me?
Yeah, I can hear you very well.
Okay, ma'am. Yes. For whatever reason, I purchased my book. As you can see, Amazon sent me the wrong book, so I returned it.
Okay, great.
And so I went to Pearson, which I believe is the most disgusting poor publisher ever.
Okay, what happened at Pearson?
Well, I purchased the book. It's $54.99, right? It's in.
Did you purchase the book or the access code? What did you do exactly?
I purchased the access code. I believe it's the ebook.
Yeah, the access code. Make sure you get the access code.
Okay, so I got it, and for whatever reason, ma'am, I couldn't get through. I couldn't download it. I couldn't read it. I couldn't do anything.
Okay, and so when you called the customer service, what happened?
They told me that they couldn't do it, and they sent me back to technical support. And being a technical support, they say, I'm gonna transfer you to somebody else. And so I gotta call them right now after I'm finished talking with you
Okay.
to get this done. Well, here I heard somebody say that the homework was not on my lab math.
I will put it, don't worry about that. Once I
Okay.
finish with you, I will check that out. That's not an
Okay.
issue.
Okay, so I checked that for something happened and I was able to log in and I purchased my math and I got the 24-month. And
Good.
I had the same problem. I could not get, I was only able to see it because someone was helping me online, but then we log off and then I tried to get in and I couldn't see, and I was able to see one more time my lab, but I didn't see any homework. So I'm asking you to please work with me, ma'am. I gotta call them again to see if I can get access to my book.
But the only thing I can do, since you have to work with Pearson, because I don't know how to help you technically.
Yeah, ma'am. I know this is not your fault, ma'am. But
Right. So I want you to call. I'm gonna put the homework back. I'm gonna check and make sure that the homework is on my MATLAB. Actually, why don't you guys stay with me? I can fix it immediately.
Okay. And I apologize for
No, you're fine. You're fine. I want you to get started, Freddie. That's not a big deal. I want you to get started.
And then that's why I've been emailing you, and I am sorry.
That's okay. Don't worry about that. Don't worry about that.
And thank you for checking your email on the weekend. I appreciate it.
No problem.
My behalf and everyone that you helped to. I'm sorry for being a hemorrhoid.
Don't worry about that. I just want you to get going.
And so you say that on the book, we start on chapter 6, right?
Yes. Yes.
I will be I will be emailing you today with the rest of my uh, situation and letting you know where am I. So
Okay.
I want to thank you for your understanding and
All
your
right.
kindness, ma'am. I thank you so much, Doc. I'm very frustrated and disgusted with Thurston.
So you cannot see the site at all, or can you?
Well, I can see the site, right? But when I try to log in, it tells me that my password is not correct. And so I changed the password, no exaggeration, man, like 200 times yesterday. And I still have the same problem. And nobody's able to help me. So I'm about to call them again. Hopefully they have someone knowledgeable about it there that can, actually help me and know what they're doing, because I need the book. I already paid for it. I already paid for my lab.
Yeah, yeah.
And I don't have access to it. It's not like, I find the money in the street, I go to work. And so they should provide wonderful service, but it's a pretty disgusting, poor, unprofessional service. I apologize about that. Are you there, ma'am?
Yeah, yeah, yeah. I'm checking what's going
Okay.
on.
Oh, one more thing, ma'am.
Yes.
When I entered your professor code,
Yeah.
somehow the system told me that it was invalid, that I had to contact you. And then I tried later on and it went through. So it was something wrong with the website or something.
Hmm. So what are you gonna do now? Are you gonna go back to Pearson?
I gotta call them, ma'am. I need the book. I already paid
Okay.
for the
All right. So
service.
call Pearson, and I will need to fix the homework myself because something is wrong with this site now.
Okay, doctor.
Okay.
Listen, I will
Yeah.
email you
Go
and I will let
back,
you know
and
about my
in the
situation.
meantime, I will fix. I don't know why the homework is not showing. Last semester I didn't have any issues, so I have to go back and check why the homework is not showing. Okay.
Okay, ma'am. I will
All
let you
right.
know about my
Okay.
situation.
All right.
Thank you, ma'am.
Sure. Bye bye. Any other
I wanted to-
question? Jacob and Andre?